Okay. So my name is Henry Dykhne. This is my master's seminar, Automated Generation of Dynamic Occlusion-Caused Collisions. Here's the roadmap for today. I'm going to talk to you about scenario-based testing, and I'll talk about some of the gaps in that and how our research pertains to it. We'll look at the prior work related to our research, and we'll talk about the research contributions that we provide. We'll take you through our dynamic occlusion typology, and then we'll take you through the nuts and bolts of how our generation technique actually works. Finally, we'll answer some questions about the quality of our generation technique, and then we'll wrap up. Okay, so scenario-based testing is one of the main ways that we try and verify the safety of autonomous driving systems. Before you put an autonomous driving system on the road, you have to test it in simulation. But testing every potential corner case is very difficult. If you want to do scenario-based testing, you need to get the scenarios from somewhere. And you've got basically two major areas you can pull from. Naturalistic driving data sets, which means you put a camera or sensors onto a vehicle and you pay someone to drive it around town for a couple thousand hours. It's slow to collect, it's expensive to collect, and you could drive potentially for an entire lifetime and not actually get into a critical scenario. If you test a system based on naturalistic driving data sets and nothing else, you're not going to be testing it against the most difficult critical scenarios. The antidote to this is handcrafted scenarios. You get an expert who knows what a difficult scenario is. That expert then enumerates all these scenarios and then builds them by hand. But it's still slow. You're still doing it one by one, so it's expensive. And there's no guarantee that you're going to capture all the edge cases. And now that you're doing everything by hand, instead of getting real recorded scenarios, there's no guarantee of realism. So we turn to automatic generation. We want to generate tons and tons of these scenarios automatically, so we can explore this scenario space a lot more quickly, and ideally find the scenarios that we might not think of creating manually. If you do a quick search for automatic scenario generation on autonomous driving, you'll find well over 1,000 results on IEEE. But if you look specifically for occlusion scenarios, you'll have difficulty finding more than 10 papers, which is really a shame because all the problems I just mentioned go double for critical occlusion scenarios. They're even more rare naturalistic data sets, and they're even more complex to reason about because now you have to coordinate the movements of 3 vehicles to cause an occlusion. And to cause an occlusion that's actually going to result in a collision. Prior work in causing occlusion-caused collisions, or occlusion-related scenarios, is a ReasonNet, which mostly focuses on generating scenarios with vehicles running red lights, or pedestrians running out of occluded areas across many intersections in Carla, which is a simulation environment. Cutout scenario generation, this paper focuses entirely on the cutout scenario, where you have a vehicle quickly change lanes to get out of the way of a vehicle in front that is stopped, which means the vehicle behind the vehicle it just cut out has no time to react and crashes. This paper does a lot of work to try and find which scenarios and which parameter ranges are necessary to create realistic ones, but the paper doesn't actually bother generating any scenarios, leaving it to future work. The next 2 papers focus entirely on pedestrians running into traffic out of occlusions. And then perhaps the most closely related work, Maximilian Kahn's I Know That You Cannot See Me, which was actually done in this lab, and it's the work that a lot of ours is built on top of, tries to generate occlusion-caused collisions between vehicles across a single intersection, the Uni-Weber intersection. So the major advancement that we try to create here is we try to generate across more intersections, we try to generate a wider variety of occlusion-caused collisions, and indeed we try to create a typology of all types of collisions to try to generate as many of them as possible. Ideally, if we can generate all of them, we've got full coverage. So, our contributions. We create a novel typology for categorizing dynamic occlusions across a variety of road geometries. We create a set of techniques for automatically generating dangerous dynamic occlusions. And we create an open source tool for the generation and analysis of OCCs. And from now on, we'll try to stick to OCC because occlusion-caused collision is a bit of a tongue twister. To our knowledge, no other works have attempted to both categorize and generate all types of dynamic occlusions across all possible intersections. The research questions we're interested in are mostly based around how good our generators are. With what frequency can we generate these OCCs? If we can only generate one, then we might as well do it by hand. We're interested in what the variety of OCCs are that we can generate, because if we're generating 1 million OCCs but they're all exactly the same, we might as well just make one. We're interested in the severity, because we're interested in the kind of damage we can cause for these OCCs. And we want to know what happens if we improve the reaction time of our drivers, because ideally these OCCs should be robust to faster reaction times. You should require better planning instead of just being faster on the trigger. So we get to our typology. Dynamic occlusion patterns are described by two pieces of information: the relative motion of the conflict vehicles, that is, the two guys that are going to crash into each other, and the relative motion of the occluder to one of the conflict vehicles. We have 23 types here, but we only tried to generate 19 of them, because head-on collisions are simply not possible to generate within the road surfaces that we have within our data set. There's no lanes that go head-to-head in our data set. So we focus on cross, conflict merge, and conflict diverge scenarios. In each cell, we have an example of what a scenario like this might look like. Let's go into a little bit more detail about how this typology works. We have our two conflict vehicles and our occluder, which is signified by this circle. So these are sequential to one another. They're going in the same direction. Neither of them are going to diverge. Our occluder is diverging, which means our type is sequential diverge. Next example here is we have two conflict vehicles, which are going to collide at this conflict point where they cross over each other. So they're type cross, but let's look at what the occluder is doing. Well, it's sequential to this vehicle, and it's going to cross this vehicle. So it's both types at once. Our typology means that some scenarios can have multiple types. And what this means is that if you're testing relative to some particular vehicle or system under test, then you can label everything with respect to that vehicle as it's situated in that scenario. Before we move on to how we actually generate the scenarios, we have to touch on the notice system. No person reacts instantly, and indeed no automatic system reacts instantly. Even the really fast automatic systems often have to register an object for several frames before they pass it to their actual planner in order to root out false positives. In order to be noticed, you must fulfill two of the following criteria. You have to be visible or already noticed at the beginning of what we call the uncloak window, which is just the reaction time that people have. It includes surprise that people might have before realizing that I have to hit the brakes. And the notice threshold. You have to be visible for at least the amount of time steps in the notice threshold. And what this means is that if you are visible for just a brief moment, just an edge of you appears from behind somebody else, you're not going to get noticed, because an automatic system would rule that out as a false positive, and a human wouldn't even notice. On the other hand, if you get blocked for a brief second by another vehicle, we're not going to forget that you exist. If you appear after a second of being blocked, then we're going to recognize you immediately. We haven't forgotten about you. In order to be passed to the planner at a given time step, you have to be both visible and noticed. Okay, a couple more steps before we jump into the nuts and bolts of how we put these scenarios together. We have a new plan, which is a simulator we're using to test all this stuff. It's lightweight, it's extensible, which means we can modify it such that it's capable of simulating occlusions, because originally it's simply not capable. We can integrate our special notice system into this to simulate reactions, and we can add a system for modifying our scenarios en masse. The main advantage of NewPlan is it comes with a massive data set of pre-labeled scenarios, so we can instantly pull out only the scenarios that run on intersections, or scenarios where we're only trying to do left turns if we're interested in that. And that makes testing a lot easier. And it also gives us a whole bunch of planning-specific metrics that we can track. In order to figure out who's going to drive our vehicles, we simply look towards who got the best scores on the NewPlan challenge in 2023. NewPlan won the gold medal. It blew everybody else away in every category. And the best part is it used a very simple, interpretable technique that was not machine learning based. It was simply rule based, mostly central line following. And that gives us a couple of advantages. Number one is it's predictable, so we can figure out what's going on during testing. Number two is it's the strongest competitor, which means that if we're tripping this thing up, then we're finding faults in a strong planner. And number three is when it finally does crash, we can be pretty sure that it crashed because of the occlusion and not because it did something random, like a machine learning planner might. Okay, to the actual generation. We use a dual filter generation technique. We take our scenario from the many scenarios in the data set, we inject conflict vehicles and occluders, and then we simulate that scenario with occlusion enabled. We filter all of those scenarios for only the ones where ego actually collided with another vehicle, and we simulate again, this time without occlusion. We finally perform a final filter for only the scenarios where ego did not crash. So we crash under occlusion, but as soon as we remove the occlusion, we do not crash, which means the occlusion is most likely what caused the crash, since that's the only difference. This system is adversarial, which means it generates occlusion specifically tailored towards the planner under test. In order to generate the occlusion-caused collisions, we use 4 types of OCC generators, each based on a relative conflict movement type. The benefit of using 4 instead of just having one big one is that it lets us tailor each generator to each type of occlusion-caused collision more easily, and it also lets us examine which scenarios are hard to generate. It also lets us take advantage of our modular system where anyone can create a new generator and just put that in and have it run and make new scenarios. I won't take you through all 4 of them because they're all quite similar. I'll just take you through how the cross OCC generator works. In step 1, we're going to remove all vehicles that are not ego. This is optional, but the reason we do it is because it increases the odds of us generating exactly the type of scenario we want, instead of ego crashing into something else unexpectedly. It also makes it easier to generate scenarios in general, because with fewer other vehicles taking up space in the road, we have more potential areas where we can place our own. So it's gone. Then we get the ego route plan. Ego in this case is our gray vehicle, and its route plan is the arrow. It's telling us where it's going. We select only the connectors which cross a lane connector in ego's route plan. So this lane connector, turning to the left, is an ego's route plan. This lane connector is crossing that lane connector. This lane connector is not crossing, it's diverging. So for a diverge generator, we choose that one. But for a cross generator, we're choosing the one at the bottom. For each conflict connector, we calculate the conflict point, that is where they cross, and we inject the vehicle in several locations, giving us several different options, based on several different starting speed offsets. We inject the vehicle such that that vehicle and ego will reach the conflict point at roughly the same time, giving us the best chance of causing a collision. So we inject the vehicle, we verify that the agent is not already occluded, because if it's already occluded, we're done. We don't have to inject an occluder. We can just pass this off to be tested. But in the unfortunate scenario where it's not already occluded, we have to do it ourselves. We generate an FOV polygon, which shows us the field of view towards this new conflict vehicle that we have just injected. And this gives us an area where we can try to inject occluder vehicles, which will ideally block the line of sight. But if we just start injecting here randomly, we're not going to end up with very realistic injections. Instead, we retrieve all the lanes and lane connectors in the local area that don't have a red light and prune them with the FOV polygon. We're only grabbing the areas inside that polygon. And since lines aren't useful for us, we want points. We discretize those lines. And these new spawn points are the ones that we're actually going to try and inject something in. We filter out the spawn points that are too close to other obstacles, like the edge of the road. And then we start testing. We inject the vehicle at each spawn point. We ensure that our new point is not too close to a previous successful injection, because we don't want to have a million scenarios that are exactly identical. And then we have to generate the details of how fast this new vehicle is going and what its final goal is, so where it's trying to get to. The speed is generated generally by looking at what speed other vehicles in the area are moving. So if other vehicles in the same lane, or the lanes leading up to it or in front of it, are going at a certain speed, that's usually a good hint that copying that speed is a great idea, so that we won't crash into them. If there's no other vehicles in order to give us a hint about speed and goal, then we simply set that speed to the speed limit. Ideally, we want these vehicles to be moving quickly, increases the odds of a collision. So we inject the occluder, we verify that the occlusion actually happens, and we perform a short time to collision test. Basically, we don't want them to immediately crash into each other. We want enough time for them to see that there's a vehicle, for them to have enough time to react to it, and then make a decision. If successful, then we submit this new modification. So let's have a look at an example of a generated scenario. I'm going to pause it right here. E goes in white, our occluder is in green, and that small vehicle at the back here, it's going to become more visible later, in black. I know it's hard to see, but it'll become easier to see later. Is going to be our conflict vehicle. Now, we've modified this visualizer so that we know when a vehicle is occluded. If the interior is black, it means that we're occluded. If the border is black, it means that we are unnoticed. So if you want to be reacted to, you got to be all green. Okay, let's move forward a little bit. Ego is making a right turn. This vehicle here is making a left turn. They're going to merge together. And this occluder is diverging from ego, is making a left turn. We've cleared the occlusion. The interior is green. We're visible, but we're not noticed yet. The person in this vehicle is still reacting, he's still surprised, he's still scared, he's still got to put his foot on the actual brake.
What's the reaction time?
We've chosen a reaction time of 1.5 seconds.
Okay.
Literature has shown that this is quite common for people who are surprised to vehicles disappearing. So, we finally noticed the vehicle, but it is far too late to actually do anything about it. And the collision occurs. Now we run the scenario again, but this time we pretend all the vehicles are made of glass. And ego knows immediately that it's got to slow down, it's got to hit the brakes, and no collision occurs. Okay, back to our research questions. These are going to help us evaluate how good these scenarios actually are and how good our generators are. We're interested in what frequency we can generate these OCCs with. We're interested in the variety of OCCs we can generate, and then we're going to look at the typology coverage we're able to achieve and the variety of different intersections that we're able to achieve it on. We'll look at the severity of the OCCs that we can generate via the delta V and the angle of impact. And we're going to look at what happens when we improve reaction time. Are these scenarios robust to a better reaction time? Okay, generation efficiency. Where is my pointer? On the left here, we have reduced and full. Previously, I mentioned that removing all other vehicles before we inject anything was optional. Reduced means we removed all vehicles. Full means we have kept them in. We're interested in two columns here. OCCs divided by the initial number of scenarios we put into the system, and OCCs divided by a number of generated scenarios that we've created. This is going to be a measure of our data efficiency, how much data we have to shove into the system to generate a certain number of OCCs. And this is going to be a measure of our computational efficiency, how many scenarios we have to actually have to spend the time running, which is the most expensive part of the process by far, versus how many OCCs we generate. And what we find is when it comes to data efficiency, cross scenarios do best. And the main reason here is because we're able to generate so many more scenarios to test, just because there's so many ways to cross past each other in an intersection. In computational efficiency, sequential scenarios do best. And this is because they simply have a very high chance of being successful. There's very little time to react in a lot of these scenarios, which makes them have a very high chance of actually working out. Compared to previous generation techniques, specifically Maximilian-Kahn's method, we are roughly on par in terms of data efficiency, or better, for almost every single generator, except for the diverged generators. Although I would note that Maximilian-Kahn did not actually generate any diverged scenarios whatsoever using his technique. In terms of computational efficiency, we have a large improvement across all possible generators. Maximilian-Kahn generated 105,000 scenarios and got 80 OCCs out of it, whereas most of our generated scenario numbers are much, much smaller compared to the number of OCCs we get. In total, and this represents about 4 hours worth of computational time, which is not very much, we ended up generating about 110 scenarios. And if we were to spend all that time generating cross scenarios, we'd end up with probably closer to around 300. Now the typology coverage. We created that typology so that we'd have something to shoot for. We want to get as many types of collisions as possible. We end up achieving roughly 11 out of 19 of these scenarios. We find that diverged scenarios are actually quite difficult to generate, precisely because of the specific geometries you need, lane geometries, to make these occlusions possible. And you have a similar story for the occluder parallel collisions. You need very specific lane geometries to make those scenarios possible. But when we look at only the scenarios that are possible in a two-lane cross intersection, we end up with a better coverage, roughly 8 out of 12 possible scenarios. We've been able to generate at least one everywhere we have a check mark over there. And so we end up with a much improved variety compared to prior work. Second measure of variety we have is the unique intersection generation. If we generate everything on a single intersection, then we're doing no better than prior work. But it's good to see here that these 22 OCCs that are sequential are split across nine unique intersections. For merge scenarios, it's a similar story. The 12 we're able to generate happen across 10 unique intersections. For diverge, the 7 is split across 5. And for cross, we're able to generate a lot more scenarios per intersection. We're able to generate 73 OCCs across 10 intersections. Okay, collision severity. There's a couple of charts here that we need to go through to understand how we measure severity, but they're not particularly complicated. The first is the AIS codes. This is going to tell you how much it's going to hurt if you get into a collision. Number 1, superficial laceration. Number 6, you're not waking up tomorrow. Well, we don't use these to categorize collisions. We use severity codes. And severity codes tell you the probability, or rather, whether you have a greater than 10% probability of having an AIS 1 to 6 injury, but not S2 level. In order to determine what kind of severity code you have, we have delta V thresholds. And delta V here refers to the speed before the collision compared to the speed after the collision. We use a ratio of the two vehicles' masses, as well as the impact angle, to determine what the speed is going to be at the end of it. And compared to prior work, we assume both vehicles are going to be of roughly the same mass. Prior work assumed that the other vehicle, not the non-ego vehicle, would be much, much heavier in order to be more conservative, to try and capture as many injuries as possible. But in this case, basically all our collisions happen between equally massed vehicles. And so keeping the masses equal gives us a more accurate representation of the kind of injuries we'll be causing. So we go to our thresholds. front to back, which has higher thresholds because you end up with more crash structure on the front, compared to the side where the crash structure is your elbow. And now we have the information to be able to understand this graph. Severity class 3 is pretty much entirely occupied by cross collisions. And that's because you have vehicles coming head on at each other, hitting each other on the side, and at very high relative speeds. Compared to the other scenarios, whether you're merging, diverging, sequential, both vehicles are pointing in the same direction and roughly headed in the same direction. Delta V is going to be much smaller. Merge scenarios also have a good chance of resulting in a side-on collision, but divergent sequential scenarios are almost always going to be front to back. And that's not speculation. We actually have these graphed by the angle and delta V. Our cross collisions are spread out in a wide angle with a little bias towards the right because the left turn collision, where you're turning towards the left and you get hit by a vehicle coming straight through, is one of the most common collisions we can generate. Merge scenarios have the hits spread out, but at a much slower speed because you're both going in the same direction. And sequential and divergent scenarios are all front to back. Finally, we get to the reaction time ablations. Here, we're reducing the reaction time of ego. We're keeping everybody else at the same reaction time, and we're making ego faster. We're simulating an autonomous vehicle driving around other human drivers. And as we can see, some OCCs are no longer OCCs. A faster reactor is able to evade some of these, but not all of them. Some are robust, some survive the cull. In particular, cross scenarios, which have a very high closing speed, are the hardest to react to quickly, and so most of them end up surviving. Our second table here has everybody else's reaction times brought down in line with ego's new better reaction time. So ego's reaction time is left at that good new reaction time at half a second, and then we bring everyone else in line. We're simulating an autonomous vehicle driving around other autonomous vehicles. And again, cross and merge scenarios get culled a little bit. Some of them don't survive. In particular, we notice the sequential and diverge scenarios don't get culled at all here. And the reason for that is that the other vehicle in this scenario is ahead and it's stopped. It doesn't have a whole lot of agency, except maybe being able to accelerate a touch faster, and whether or not it gets rear-ended. And so those scenarios don't experience any kind of degradation whatsoever. But cross and merge scenarios do. Limitations in future work. The achieved coverage isn't complete. There are still some X's in our coverage. Future work could work to extend the coverage to cover all these types of scenarios. In particular, since the main problem is the fact that we don't have the exact lane geometries we need to generate the ones we're missing, you could try to manually generate these lane geometries and just shove them in and see if these scenarios can, these generators can create what we need automatically. Alternatively, you could look at trying to modify the generators themselves. Other limitations involve the fact that we only cause collisions with vehicles. Future work should look to include pedestrians and cyclists in our typology. And our final limitation is the fact that the agents are controlled by rule-based planners. Now this is good because all the agents are making good decisions, ideally best possible decisions. But I could very easily see a way which you can turn this into an RL problem, where the occluder has the goal of extending the occlusion. We're trying to drive in a way that tricks the other vehicles into crashing into one another. I think that's a very interesting extension of his work. So, in conclusion, we provide a comprehensive typology to label dynamic occlusion scenarios between two vehicles. We develop a general technique for the generation of OCCs, as well as a specific set of generators catered to each type. We provide a tool for the efficient generation of OCCs on wide amounts of intersections, and a testing of ADSs in the occluded regime. And we provide a thorough analysis to show that our tool is capable of generating scenarios that are both critical and diverse. In the future, we hope this contributes to ADS verification pipelines in order to make sure that future autonomous driving systems are occlusion aware and occlusion safe. This thesis simply wouldn't be complete today if I didn't have help. I'd like to thank, in particular, Shay, Anthony Cardozo, and James Riddell for helping with the actual implementation of the multi-agent planner and the occlusion injection system. I'd like to thank my supervisor, Dr. Christoph Sarnecki, Dr. Sean Sedwards, and Dr. Bharat Abelzad for their guidance over the course of this research. And I'd like to thank Dr. Nancy Day and Dr. Stephen L. Smith for attending and agreeing to be my readers. Finally, I'd like to thank everybody in the WISE Lab who I've had the absolute pleasure of working with for the past 2 years.